Hello, I'm Will Thomas, the Spencer Wirt Director of Research in History, Policy, and Culture at the American Institute of Physics. Welcome to this Lyne, Starling, Trimble lecture with Professor Bruce Hunt, titled The Victorian Cable Empire and the Making of Maxwell's Equations. There are a few things to be aware of before we begin, as shown on the screen. First, all attendees will be in listen-only mode throughout the lecture. To submit questions for the speaker, please use the Q&A function. If you are having technical difficulties, then use the chat feature. Finally, closed captions are available for this lecture. To turn them on, click the CC icon at the bottom of your Zoom window. Next, let me introduce our speaker. Bruce Hunt is a professor of history at the University of Texas at Austin, where he teaches courses in the history of science and technology. He holds bachelor's degrees in history and physics from the University of Washington and a PhD in the history of science from Johns Hopkins University. And he is a fellow of the American Physical Society. He's the author of Imperial Science, Cable Telegraphy and Electrical Physics in the Victorian British Empire, Pursuing Power and Light, Technology and Physics from James Watt to Albert Einstein, and The Maxwellians, as well as many articles on the history of 19th century physics and technology. Please join me in welcoming Bruce Hunt.
I'd like to thank the AIP for inviting me to give this Trimble lecture today. It's a real honor. Today I want to take up the relationship between science and technology. A lot of people think of technology as simply applied science, with new technologies growing pretty directly out of purely scientific discoveries. And no doubt this has often happened. But today I want to flip things over and look at how technologies can sometimes stimulate and shape even the most fundamental scientific work. I'll do this by looking at one of the great scientific achievements of the 19th century, the formulation of the laws of electromagnetism, what we now know as Maxwell's equations. These equations now show up on t-shirts, like this well-known one, "And God said," and this one, where Maxwell said, "And there was light." And we also find these equations on a plaque next to the statue of James Clerk Maxwell that was erected about 15 years ago near his birthplace in Edinburgh. The American physicist Richard Feynman once said that from a long view of history, there can be little doubt that the formulation of these equations will be judged as the most significant event of the 19th century. That's a stretch, but it reflects the high regard physicists have long had for Maxwell's equations. Maxwell's theory, as expressed in these four vector equations, has become one of the most important theories in all of physics, governing everything from the behavior of light and other electromagnetic waves to many of the workings of matter. The technological uses of this theory for radio, mobile phones, the electric power system, these have transformed modern life. Today, I want to look in a concrete way at just where Maxwell's equations really came from, at how and why they came to look the way they do, and why they were formulated in Britain rather than, say, Germany, and why in the second half of the 19th century. And particularly, I want to look at why it was Oliver Heaviside rather than James Clerk Maxwell who in fact cast these equations into their most familiar form. To answer these questions, we'll need to look beyond the strictly scientific context of 19th century electrodynamics and examine the broader material and technological circumstances of the time. We'll need to look to the rising electrical industries of the 19th century, particularly the first of these industries to become important, telegraphy. By putting electrical theory into this context, we'll be able to place it where it belongs among the vast technological changes of the second half of the 19th century. I will argue that Maxwell's equations were cast into their definitive and most widely used form, the four vector equations we see here, largely in response to the demands and opportunities presented by cable telegraphy, one of the characteristic technologies of the British Empire in the Victorian era. Now, not long after Heinrich Hertz first demonstrated the existence of electromagnetic waves in 1888, Oliver Lodge, one of Maxwell's main British followers, declared that with this confirmation of the electromagnetic theory of light, the whole domain of optics is now annexed to electricity, which has thus become an imperial science. Well, electricity was an imperial science in a more literal sense as well. It was the foundation of the global cable network that sustained Britain's imperial power. A glance at a 1901 map of the world's submarine cable routes shows how pervasive that network really was. Most of these cables were owned by British companies, and almost all of them were manufactured and laid by British firms. The global cable network was overwhelmingly British from the time the first successful undersea line was laid across the English Channel in 1851 until the industry began to decline after the First World War. Today, of course, with fiber optic lines, the undersea cable industry is really bigger than ever. There's no great mystery behind Britain's dominance of the world's submarine cable industry in the 19th century. Britannia ruled the waves, and it was only natural that she should seek to extend that rule beneath the waves as well. As a maritime trading nation, and as easily the leading commercial, industrial, and imperial power of the day, Britain had both the greatest need for cables and the greatest capacity for laying them. The network of undersea cables has often been called the nervous system of the British Empire. Information flowed in along the cables, and commands flowed out. By the last third of the 19th century, cables had become the favored channel for rapid overseas diplomatic, military, and commercial communications. They bound the empire more closely together and helped Britain secure its continued political and commercial preeminence. In return, Britain's imperial and commercial power helped reinforce its dominance of the cable industry in some quite direct ways. For instance, Britain's control of Malaya and Singapore gave it an effective monopoly on the trade in gutta percha, a natural plastic derived from the latex of certain tropical trees in the area that was the favored material for insulating cables. Hundreds of tons of gutta percha went into a long cable, and since foreign companies were unable to obtain such large quantities, they were effectively shut out of competition. Now, how did Britain's virtual monopoly on cable telegraphy affect the science that was done in Victorian Britain? Submarine telegraphy was one of the high-tech industries of the day. It required specialized expertise, and in this the dominance of British engineers and scientists was almost total. They were the ones who designed and manufactured the cables, who found ways to lay them safely at the bottom of the sea, and who devised techniques and apparatus for signaling effectively through them. All of this, especially the signaling, exposed British physicists and engineers to effects that no one else had ever encountered, and had a strong effect on the way they conceived of electrical phenomena. In particular, this experience with cables led British physicists to pay special attention to electrical propagation and to electromagnetic waves, phenomena that were leading features of Maxwell's theory, especially in the definitive form it took in the 1880s. Now, I could use any of several episodes to illustrate the ties between cables and British field theory. Michael Faraday's participation in early cable tests in 1853 and their effect in drawing attention to his theories. The deep involvement of William Thomson, later Lord Kelvin, in the first failed Atlantic cable of 1858, in the two successful ones of 1866, and in a string of other cable projects over the next 40 years. Or we could look at Maxwell's own work on the British Association Committee on Electrical Standards that in the 1860s established the value of the ohm, a project that was launched to serve the needs of cable engineers and that went on to have major effects on telegraphy, on the rise of laboratory physics, and on Maxwell's own work on his electromagnetic theory of light. But today, I want to focus on a slightly later episode, Oliver Heaviside's recasting of Maxwell's theory in the 1880s into the Maxwell's equations that we know today. Here again is this set of four vector equations, here expressed in a space free of charges and currents, so it really simplifies it and shows the symmetry very well between electric force E and magnetic force H. When people talk about Maxwell's theories nowadays, these equations are generally what they have in mind. But you won't find this set of four equations in Maxwell's great treatise on electricity and magnetism of 1873. Maxwell's chapter on the fundamental equations of the electromagnetic field instead contains a list of about 13 main equations, depending on exactly how you count them, about 13 main equations involving the vector and scalar potentials and several other quantities that do not appear at all in this famous set of four. The compact set we now know as Maxwell's equations has in fact been taken from papers that Oliver Heaviside published in the mid-1880s, mostly in an electrical trade journal called The Electrician. Moreover, Heaviside cast Maxwell's equations into this particular form in order to make them a better tool for tackling telegraph problems. Well, who was Oliver Heaviside? He was a very unusual man. His best friend once described him as, quote, a first-rate oddity but never a mental invalid. Born in 1850 in what he later described as a very mean street in London, Heaviside's early life was almost literally Dickensian. Charles Dickens, in the unhappiest part of his own childhood, had lived in lodgings just around the corner from the house in Camden Town, where the Heavisides later settled. Though born and bred up in it, Heaviside later said, I never took to it, and was very miserable there, all the more so because I was so exceedingly deaf that I could not go and make friends with the other boys and play about and enjoy myself. A bout with scarlet fever had damaged his hearing when Oliver was very young, and though he recovered from most of his deafness by early manhood, it left a permanent mark on his personality. He was always a loner, and he spent most of his time reading and studying. He had few real social skills, and though in later years he maintained a wide correspondence with other scientists, he had remarkably little direct contact with people outside his family after he was about 25. He had a sharp wit, which showed itself even in his mathematical writings, but his gift for sarcasm helped land him in several bitter disputes. Heaviside attended the local grammar school in Camden Town in North London, and he showed early talent in science. But his parents had no money to send him to a university, so when he was 16, he left school and set out to find a job. He was soon sent north to Newcastle to become a telegrapher, a move that would set the course for all of his later work. That Heaviside went into telegraphy was the result of a fortunate family connection. His mother's sister had married Sir Charles Wheatstone, one of the inventors of the telegraph. As Wheatstone's poor relations, the Heavisides looked to Sir Charles for help in finding careers for their sons, and he obliged. Oliver's brother Charles became an expert on the concertina, another of Wheatstone's many inventions, and went into the music business, while another of his brothers, Arthur West Heaviside, we'll meet again later, became Wheatstone's telegraphic assistant and later ran one of his local telegraph companies in Newcastle. After Britain nationalized its inland telegraph companies in 1870, Arthur became a leading engineer in the post office telegraph system, and he continued to play an important part in his brother Oliver's career. Oliver started work in 1867 as Arthur's assistant, and then in 1868 he was hired to help with testing the newly laid Anglo-Danish cable across the North Sea. Here's a map showing the cables around the British Isles. The Anglo-Danish cable, number 18 there, is the one that runs straight across from Newcastle to Denmark. In the late 1860s, when Oliver Heaviside got his start in it, the cable industry was booming. The completion of the first successful Atlantic cables in 1866 was followed by a string of big cable projects, especially lines connecting Britain to India and the Far East. The Anglo-Danish cable was a key link in the Great Northern Network, which ran from England across the North Sea and Russia to China and Japan. It was one of the relatively few cables that wasn't British-owned. The Great Northern Company was Danish. But significantly, the cable was manufactured, laid, and tested by British contractors. It was while testing the newly laid cable, checking it for faults, and adjusting the sending and receiving apparatus that Heaviside was exposed to the practical problems of telegraphy and the peculiarities of working a submarine cable. Here we see a cable testing room from the late 1860s with the batteries on the floor, the galvanometers on the table. Cable testing rooms like this one were among the most advanced and best equipped electrical laboratories in the world in the 1860s. A lot of instruments and measuring techniques, even the basic units of volts, amps, and ohms that we still use today, were first developed by and for British cable engineers, and only later made their way into academic physics laboratories. Oliver Heaviside was thus exposed to the leading edge of electrical technology and science in the 1860s, and he learned far more about the actual behavior of magnets, currents, and coils while working on the cable than he would have had he been sent, say, to Cambridge or to most other universities of the day. The most important phenomenon that Heaviside encountered in the testing room was the distortion and blurring that signals suffered when they were sent down a long cable. This was a serious problem, since it put a limit on how rapidly a cable could be operated, and so on the amount of business it could handle. Here are some traces of cable signals sent through different lengths and types of cable, from the sharply defined ones that you see at the top to the rather stretched out and blurred ones further down as the capacitance of the cable is increased. Telegraphers first noticed distortion on underground lines around 1850, and it became a major problem on long submarine cables that were laid after the mid-1850s. The electrical characteristics of cables, mainly their high capacitance, caused the sharply defined signals put in at one end to blur and run together by the time they got to the other, so that signaling had to be done relatively slowly to keep the signals from becoming indecipherable at the receiving end. This problem was especially acute on long cables, since the amount of blurring increased with the square of the cable's length. Some early cables could be worked at only 2 or 3 words per minute, though the early Atlantic cables could handle about 15 words per minute. The Anglo-Danish cable was better, mainly because it was shorter. Depending on the sending and receiving apparatus that was used, it could handle up to 70 words per minute on test runs and didn't have much trouble with the usual commercial rate of 20 to 30 words per minute. Still, this was much less than overhead landlines could handle, and especially compared to the hundreds of words per minute that were routinely achieved by the Wheatstone automatic telegraph transmitters that became standard on the main British landlines in the 1870s. Now, Heaviside was familiar with these automatic telegraphs, another of his uncle's inventions, and he was frustrated by the impossibility of using them to their full advantage on the Anglo-Danish cable. Engineers could improve cable signaling rates to some extent by using more ingenious sending and receiving instruments, but by the time Heaviside started, it was clear that the electrical characteristics of the cable itself set fundamental limits on the speed of signaling that could be achieved. As the pace of world communications increased in the last third of the 19th century, that limit became less and less acceptable. British engineers tried hard to find ways to make their cables handle faster signaling rates, and so were pushed into making a close study of the causes of distortion and of the fundamental question of just how electrical signals travel along a cable. I want to emphasize that this was a specifically British problem, since it was the British who ran the world cable system. You can see here another cable map with the British Empire shown in red. British engineers and physicists had to deal with distortion problems on submarine cables that their German, French, and American counterparts simply didn't face. The telegraph lines in Germany, France, and the United States ran overland. Most were little more than bare wires strung from poles. Such overhead landlines are much simpler electrically than our submarine cables. Their capacitance is very low, and consequently they show little distortion, even on quite long lines. In practice, the limits to speed on overhead lines were set by the rate at which clerks or machines could send and receive. A suspended wire could handle even very high rates of signaling without much trouble. Telegraph engineers in America and in continental Europe thus didn't have to pay much attention to propagation problems or to whatever might be going on in the space around a telegraph wire. They could treat an electric current pretty much like water flowing in a pipe and could ignore any complicated field effects. An incident in Thomas Edison's career gives a good idea of the difference between the problems of submarine cables and those of landlines. In 1873, Edison visited England to try to sell an automatic telegraph system he had developed. He demonstrated it running at 1,000 words per minute on overhead lines between Liverpool and London, and then was asked to try it on a 2,000-mile long coil of submarine cable that was being readied for shipment from a London factory. When he sent a dot through the cable, he found that instead of getting a mark on a paper tape a 32nd of an inch long as he did through landlines, he got, he said, a smear 27 feet long. If I ever had any conceit, he said later, it vanished from my boots up. Despite intensive tinkering, he could never get more than about 2 words per minute through the cable. The problems of cable propagation forced the British to pay far more attention to field phenomena than was required of their American, German, and French counterparts, and their theories reflected that difference. The connection between cables and field theory can be traced in some detail in Heaviside's career. He continued to work for the Great Northern Company for about 6 years. But in 1874, he left Newcastle and returned to London to live with his parents. Basically lived in their spare bedroom. Partly because of health problems and partly to give himself more time to investigate theoretically the cable problems that had come to fascinate him. To equip himself to attack these problems, in the 1870s, Heaviside essentially turned himself into a mathematical physicist through private reading and study. He never again held a regular job after leaving Newcastle, and he really had almost no income. His brother Arthur apparently sent him a little money, and he later got about 40 pounds a year for articles he sold to the Electrician, a London trade journal that was owned by cable interests. It was a bare subsistence, but it was enough to enable Heaviside to carry on his work, and he seemed to be happy enough with it. Now, Heaviside's great ambition in these years was to design a perfect cable that could be worked arbitrarily fast with no distortion. The standard theory of cable signaling had been worked out by William Thomson, we see here, in 1854, later, of course, Lord Kelvin. Thomson's theory treated electrical propagation as a kind of diffusion of current along the cable, on analogy to Fourier's theory of the diffusion of heat. And it gave equations describing how the current and voltage would gradually rise at the cable's far end. Thomson's theory was put to good use for many years, and it allowed cables and apparatus to be designed much more efficiently than before. But while Thomson had explained why distortion occurred and had suggested ways to work around some of its effects, he couldn't point to any practical way to lessen or eliminate the distortion itself beyond the expensive expedient of using much fatter cables with more copper and more gutta percha. In Thomson's theory, and in the experience of cable engineers, distortion seemed inescapable. But Thomson's theory was incomplete, as Heaviside pointed out in 1876. Thomson had ignored self-induction, a sort of electromagnetic inertia that opposes changes in a current. Self-induction acts much like a flywheel, and British field theorists often pictured it as due to little bits of whirling machinery in the field surrounding a wire. Here we have Oliver Lodge's representation of it from the 1880s. The rack in the middle there represents a current, and as it moves, it makes the cogwheels in the field around it spin around. For the slowly varying currents that Thomson had discussed in 1854, self-induction had relatively little effect and could be safely ignored. But for the faster rates Heaviside was interested in, self-induction had to be taken into account. Once it was, one found that the current didn't simply diffuse along the wire, as Thomson had said. Instead, this inductive momentum made the current oscillate, so that waves of voltage and current were sent surging up and down the cable. Exactly how this worked wasn't really entirely clear to Heaviside in the 1870s, but his telegraphic investigations were already pushing him into paying more attention to electromagnetic waves and the electromagnetic field. Hoping to gain a better grasp of what was going on around a telegraph wire, Heaviside turned to Maxwell's Treatise soon after it appeared in 1873. Here we see Maxwell in the title page of his famous treatise. The book was full of ideas, but they weren't always very clearly expressed. Many of Maxwell's most important ideas on the distribution of energy in the field, for instance, and on electromagnetic waves, were buried amid long accounts of miscellaneous facts and other people's views. To make matters worse, Maxwell died in 1879, just 6 years after his book was first published, and before he made much progress on revising it for a second edition. As a result, the main work of cleaning up Maxwell's theory, of deciding exactly what it meant, of extending it, and of testing it experimentally, was left to be done after his death by others, by the so-called Maxwellians, including Oliver Heaviside. In this process of revision and extension, Maxwell's theory acquired many features that, while in some sense implicit in Maxwell's original scheme, were by no means recognized or stated by Maxwell himself. The most important of these new ideas was that of energy flow. Maxwell had said clearly enough that energy is stored in the field around a charge or an electric current, and he had even given formulas for how this energy is distributed. But he never said anything really about how the energy would move around when the charges or currents changed. Heaviside looked into this question in the summer of 1884 in hopes of learning more about how energy gets into and out of a telegraph line. Using Maxwell's own rather cumbersome formulas and going through a series of roundabout mathematical transformations, Heaviside hit upon a strikingly simple result. The energy flow at a point, he said, depends only on the vector product of the electric and magnetic intensities at that point. Here's a representation of the energy flow around a wire of high resistance, very close to the wire. The electric force, electric intensity is along the direction of the current. and the magnetic force, magnetic intensity as it circles around it. And the vector product of those gives an energy flow going into the wire from outside it. Here is another image. This image shows the energy flow from a battery to a light bulb. You see first at the top the electric field lines between the wires, and the magnetic field lines in the middle image going in circles around it. And then the energy flow, which goes from the battery through the space to the bulb. Heaviside immediately saw the importance of this result, and he began to draw really surprising consequences from it. For instance, as shown here, that the energy conveyed by an electric current doesn't flow along within the wire, as everyone had always just assumed, but instead, Heaviside said, flows through the space outside it. The wire serving only as a guide, not a pipeline. Most physicists and engineers found this idea hard to swallow, and a lot of people still find it unintuitive, shall we say. And few accepted it at first. Heaviside, however, saw it as the key to understanding and improving telegraphic propagation. It is, after all, the energy that is sent along a wire that counts, the energy to deflect a needle or to tap a key. A clear grasp of how that energy gets from one place to another was the central problem of effective telegraphy, and Heaviside was determined to follow up the clue his energy flow idea seemed to offer. Heaviside's discovery of the paths of energy flow revolutionized the way he understood Maxwell's theory and also the way he expressed it. Taking energy flow as the central fact of electromagnetism, Heaviside believed that his simple result ought to follow directly from the basic equations of the theory without requiring the roundabout derivation he had originally used. Following this clue, he worked back from the flow formula and recast the complicated equations Maxwell had given into the equivalent but much simpler form that we know now as Maxwell's equations. Here again is Heaviside's form of Maxwell's equations, here including terms for the charges and currents. These were first published by Heaviside in articles in The Electrician early in 1885. Note a couple of things. These equations involve only the electric and magnetic intensities, E and H, the quantities that determine the energy flow. They can also be written in terms of the related electric and magnetic vectors D and B and the electric current J, and that's the form we saw on the t-shirt and the statue earlier. Heaviside called these equations Maxwell redressed, and he used them almost exclusively in his own work from 1885 on. They are better suited to dealing with electromagnetic waves and other propagation problems than are Maxwell's own equations, which isn't surprising since Heaviside had specifically tailored his equations to handle energy propagation. This is a key point. Heaviside's form of Maxwell's equations is just one of many formally equivalent ways in which the laws of electromagnetism can be expressed. But it is the one best suited to treating the kinds of propagation phenomena that were Heaviside's main concern. When the announcement of Heinrich Hertz's experiments in 1888 suddenly put electromagnetic waves in the scientific spotlight, physicists quickly took up Heaviside's work and put it to use. By the mid-1890s, his equations had become the standard textbook form of electromagnetic theory. Albert Einstein learned Maxwell's theory from a textbook based quite directly on Heaviside's work, and physics students ever since have studied what are really essentially the equations Heaviside had laid down. Now, unbeknownst to Heaviside, the energy flow formula had in fact been discovered by the Cambridge-trained physicist John Henry Poynting at the end of 1883, a few months before Heaviside hit on it. That's why it's now called the Poynting flux rather than the Heaviside flux. But Poynting wasn't nearly as close as Heaviside to the problems of telegraphy and electromagnetic waves, and he didn't see really the full strategic importance of his discovery. Poynting was satisfied with having proved a nice mathematical theorem, even if the derivation was rather roundabout, and he didn't see the flow idea as a clue to the kind of deep restructuring of electrical theory that Heaviside undertook. And Poynting made no move to follow up his discovery and recast Maxwell's equations into a simpler form. That was left to Heaviside, whose struggles with cable problems had made him sensitive to anything touching on electromagnetic waves and the relationship between wires and fields. Heaviside wasn't slow to follow up the implications of his energy flow theorem for telegraphy. It led him to radically reconceptualize the function of telegraph lines, away from the old view of them as electrical pipelines and toward a new view of wires as waveguides. A wire, Heaviside said, is just the comparatively passive core of actions that really go on mostly in the space outside it. This reconceptualization completed the process Faraday and Maxwell had begun of shifting attention away from charges and currents and toward the surrounding field. Heaviside now saw telegraph signals as electromagnetic waves in space, not within the wire. They were really no different from light waves, except that they were of much longer wavelength. Heaviside later emphasized this point by declaring that telegraph wires made, quote, beams of dark light. And from this point of view, I have to say, a modern fiber optic cable isn't really so different from the old copper and gutta percha ones. Wires were still important, of course. They steered the waves from one place to another and kept them from spreading out the way ordinary light does. Also, the electrical resistance of the wire pulled energy out of the waves, out of the field, heating the wire and distorting the wave's shape. But now that he saw the waves as traveling outside the wire, Heaviside's focus was firmly on the field, and his approach to dealing with distortion problems shifted in important ways. He soon saw that if he could get the wire to draw energy out of the waves in a balanced way, he could preserve the shape of the waves and lessen or even eliminate distortion. By about 1886, Heaviside could see that he was coming close to his goal of designing a perfect distortionless cable. Here we see a picture of Heaviside and his family when they were in Devonshire around 1890. You can see Oliver just sort of in the background there, smoking his pipe, obviously a little separate from the rest of the family. That's his father and mother, father with the beard, in the middle. And the important figure for us right now is his brother Arthur, there in the gray suit and holding his hat on the side. Oliver Heaviside hit on the solution to the problem of distortionless propagation in the winter of 1886-87 while he was helping his brother Arthur with a joint paper for the Society of Telegraph Engineers. Arthur Heaviside was a leading figure in the early history of telephones in England. Among other things, he devised the bridge or parallel telephone circuit, which made party lines practical. He wanted to publish a paper on this, and Oliver agreed to write the theoretical part. Now, distortion was even more of a problem with telephones than with telegraphs. The human voice includes frequencies up to several thousand cycles per second. And on a telephone line, unlike a telegraph, you can't work around distortion just by talking slower. The attenuation and jumbling of voice frequencies and the total absence in this period of electrical amplifiers put severe limits on long-distance telephony, even on overhead landlines, and virtually ruled out working telephones through underground or submarine cables of any appreciable length. When Oliver Heaviside looked into the theory of how one of his brother's bridge circuits would affect a signal sent along it, he was surprised to find that the self-induction of the telephones along the line had a beneficial effect. This seemed odd, since it was known that a single source of self-induction on a line, a coil for instance, affected signals very badly. In fact, such coils are called choke coils. But Heaviside's mathematical theory showed that if he spread the extra inductance out along the line, it would in effect give the waves extra momentum, and so help to carry them along. The wave would still die out as it passed along the wire, but more slowly and smoothly than before, and with much less distortion. Heaviside showed theoretically that by inserting coils at proper intervals along a wire, or by adding finely divided iron to its insulation, it would be possible to load it with just enough self-induction to completely eliminate distortion. Adding even a little extra inductance could greatly improve the clarity of the signals and make it possible to telephone to much greater distances or to work a cable at much higher speeds than would otherwise be possible, and at relatively small additional cost. Heaviside was excited by this discovery. He saw that it could revolutionize both cable and telephone communications, and he later said he considered it to be his best work. Now at this point, the spring of 1887, Heaviside had completed his main creative contributions to electromagnetic theory, but he had not yet had much real effect. His theoretical work had attracted very little notice from physicists, and his practical proposals, notably loading, had not yet drawn the attention of engineers. The story of how Heaviside's ideas moved into the mainstream is interesting but rather complicated. Here I'll just sketch a few points that bear on my main argument. Heaviside's main problem was this man, William Henry Preece, later Sir William, the head of the post office telegraph and telephone system, and a powerful figure in British electrical engineering. Preece knew from experience how badly a single lump of self-induction could distort telephone signals, and he found it ridiculous to think that spreading this evil inductance out along a line would somehow give it a beneficial effect. Like most people, he was unable to follow the mathematics of Heaviside's loading theory, but he was sure its conclusions must be wrong. Moreover, Preece was in a position to make this rejection stick. He was Arthur Heaviside's boss, and he had to approve any paper submitted for publication by his post office subordinates. Preece blocked the Heaviside brothers' paper outright in the spring of 1887, and he was apparently behind the abrupt cancellation that fall of Oliver's regular series of articles in the Electrician. This touched off a bitter feud between Preece and Heaviside that was to last the rest of their lives. These problems with Preece, who was in many ways the head of Britain's electrical engineers at the time, drove Heaviside to seek a new audience, and in 1888 he found a receptive one among physicists. That spring, Oliver Lodge began to experiment with electromagnetic waves along wires, and in Germany, Heinrich Hertz was performing his even more dramatic experiments on electromagnetic waves in air. These experiments aroused great interest and focused attention on Heaviside's previously neglected papers, where physicists found that the theory of electromagnetic waves had already been very fully worked out in connection with telegraph problems. The upshot of all of this was that Oliver Heaviside rather suddenly became well known and respected, at least among physicists. His series in the Electrician was restarted, his papers were reprinted as books and closely studied. He was rather quickly elected a Fellow of the Royal Society of London, and by the mid-1890s his form of Maxwell's equations had taken its place in textbooks. The cycle of Heaviside's work, running from its roots in technology to its impact on theoretical physics, had completed its first leg. And through all of this, he was living with his parents, first in London, and then they moved above one of his brother's music shops in Devonshire, and he lived there. After his parents died, he lived alone in a house not too far away. Here we see him, he was an avid bicyclist in this period, and we see him with his bike. Now, the other half of the cycle of Heaviside's work, running from theory back to technological application, was somewhat delayed. Preece kept Heaviside's loading proposal from being tried on long-distance telephone lines in Britain in the 1890s, and he also discouraged the private cable companies from trying it on submarine cables, where in any case mechanical difficulties made it much more difficult to apply. But in America, a group of engineers at AT&T took up Heaviside's idea and had a loaded telephone line in operation by 1899. Loading proved very successful and allowed workable long-distance phone lines and underground cables to be built for a fraction of their earlier cost. Columbia University physics professor Michael Pupin, who held the American patent rights, and it's a complicated story of how he acquired those, Pupin made a fortune from loading, as did AT&T. Heaviside, however, never got a penny for his work on loading. He was bitter about this in his later years, probably as much at being denied what he thought was his rightful credit and recognition as it being robbed of the money itself. He was in fact quite proud to see how his ideas had been vindicated and won wide acceptance, both in pure science and in the electrical technology from which his work had originally sprung. There's a final irony here. One of the main areas in which Heaviside's theoretical work was put to practical use was radio. And in the 1920s, it was long-distance radio telegraphy, bouncing waves off the Heaviside layer in the upper atmosphere, that finally broke the British cable company's hold on international telecommunications. Heaviside's work was rooted in cable technology, but its uses and implications went far beyond it. To conclude, this case study of Heaviside, cables, and Maxwell's equations illustrates some simple but important general points. One is the value of looking at scientific work in the broadest possible context, not least for the light this can shed on the inner workings and content of the science itself. It might not seem on the surface that understand why Maxwell's equations look the way they do, or why they were formulated when and where they were, we should first examine the role that telegraph cables played in the British Empire. But it's only when we put the equations in this context that we can see how important problems of telegraphic propagation and energy flow were in their evolution. More generally, it's only by looking at this kind of concrete material context that we can hope to understand a lot of points in the history of science that might seem to be purely internal or determined by nature alone, and that we can get a better grasp of the reciprocal relationship between science and technology. And here, just to wrap things up, is a list of further reading on cable telegraphy, electromagnetic theory, Oliver Heaviside, and Maxwell's equations. Be happy now to take some questions.
So I guess I'll ask the first question, which is, so we've learned from, especially from Andy Warwick, that learning to think and to work with the mathematics of physics in this period is a very difficult thing, and that there was this whole culture, in particular at Cambridge, around teaching people to use it. And it seems that Heaviside operated entirely outside of that system. And so I'm curious as to, did he just take it up completely on his own, or did he have some assistance in some way?
He was a remarkable guy. He did it on his own. He never had any formal mathematical training after he left grammar school at the age of 16. And his training there was pretty, elementary. He taught it himself from books. And I got to say, Andy's a good friend of mine. I've known him for a long time. I agree with him on a lot of stuff, but Heaviside is a big counterexample to the claim that you need a sort of culture of teaching for this. Now, I don't like to fall back on, well, he was a genius, but he was a remarkably able mathematician. And he worked things out really very much on his own, with his own style, which I have to say was immensely irritating and off-putting to certainly to William Thomson, Lord Kelvin, who said, "Yo, that was just unreadable." But interestingly enough, many of his methods and techniques and way of doing things are what eventually won wide acceptance. The whole vector algebra, the vector calculus methods that are taught to physics students and everybody else are mostly drawn from Oliver Heaviside. So yeah, I mean, it's generally, I think you need a sort of community to master these things. Heaviside is the sort of great counterexample of someone who really did. I mean, he's literally working in his parents' basement practically, working all these things out purely for his own satisfaction initially. But then he shares them, and people find that they're useful, and they're taken up by others. But he had no teachers and no students, in any direct way. So he's a curious figure in that way, but a remarkably influential one in the long term.
That's extraordinary. So we have one question. I'm not sure if it's going to be practical, but maybe you can give us a little bit more of a description than you did in the talk. The question is, can you show us examples of Maxwell's original equations?
I would have to go through, flopping around through my computer here. It's all right. It's a couple of interesting points on that. Maxwell expressed most of them in Cartesian coordinates initially, much of it in terms of the vector potential, capital A as the vector, but he also used quaternions. Which were something that had been developed by the Irish mathematician William Rowan Hamilton and taken up by Maxwell's lifelong friend Peter Guthrie Tait, who wrote a lot about quaternions. And so Maxwell took up quaternions, which are kind of like vectors but more complicated. And it was Maxwell's use expression. He didn't sort of work things out mostly in quaternions, but he would then give he'd give the full gory details in Cartesian coordinates, and then he'd say, this can be expressed more compactly in quaternions, and he'd write these equations down. And that's what led Heaviside then to take those up and sort of strip them down and turn them into the vector form that we know of later, know now. I don't think I'm sort of set up to be able to show you nice images of Maxwell's original expressions. But you can find them if you get a copy of Maxwell's treatise, which you can find easily online. Just sort of, Google it up and look for general equations of the electromagnetic field, and you can see he has this long list of equations. They're mathematically equivalent. I don't want to say, oh, these should not be called Maxwell's equation. Maxwell's the guy who worked out the fundamental relationships, but then Heaviside changed, found an equivalent mathematical expression that was more compact, and as he saw it, would show the real bones of what was going on in a more perspicuous way. But yeah, it was an uphill fight for Heaviside to get people to appreciate his way of expressing things. One other side point I should make: if you were paying really close attention, you would have noticed that the version of Maxwell's equations on the T-shirts and the statue of Maxwell in Edinburgh look a little different from what I put up as Heaviside's, in that they use the so-called del cross and del dot instead of div and grad and curl, div and curl, as Heaviside did. Those are just different names for the same operations. The ones that are usually used now of del dot and del cross are from Josiah Willard Gibbs in America, who independently of Heaviside developed also a vector algebra derived from quaternions. But they're really very closely equivalent. They're, as both Heaviside and Gibbs recognized.
Okay, we've got 5 questions stacked up here, so hopefully we'll be able to get through them.
Sure.
The first is, in the 1890s, Heaviside used now we have 6. Heaviside used a variation of Maxwell's equations to give a field theory of gravity, which predicted gravitational waves 20 years before Einstein. Mm-hmm. Why was Heaviside's gravitational field theory ignored?
Because there was no empirical test of it that seemed to have any advantage over Newton's gravitation. Most of Heaviside sort of dabbled in other things, but he was very deeply rooted in electrical stuff, and so his work on gravity is kind of interesting. But he didn't get that deep into it, frankly, himself. He saw it as just a kind of applying some of the same formalisms to gravitational problems. And I got to say, yeah, part of the reason his electrical work was taken up was because people found it useful for problems that they were working on. And I don't think, as I've never seen anybody who found his approach to gravity at that point useful. And certainly they were never close to detecting gravitational waves that his theory might have predicted. So it's a nice case of sort of a precursor stuff, but it's not something that certainly was taken up by anybody else at the time, and that frankly I don't think Heaviside regarded as something that was a big deal to him either.
Okay, can you draw parallels between Heaviside and Joule as an outsider whose work was very linked to practical affairs, but who is supported by Kelvin? Is this a patronage conversation?
Yeah, I think there are some similarities. Joule is very much an experimentalist, which Heaviside had a lot of respect for experiment, but he didn't have the facilities to do much. He's basically interpreting things that other people had done, and that cable telegraphers had done. The degree of patronage that he has from William Thomson, from Kelvin, is interesting, though limited. When he was quite a young man, still working for the cable company in Newcastle, he had published a couple of papers on the mathematical treatment of the Wheatstone Bridge for measuring resistances, comparing resistances. That was published in a philosophical magazine. And William Thomson happened to be coming through Newcastle. He dropped by the telegraph office and asked to meet Oliver. And that was like a huge thing for Heaviside, young Heaviside, and very impressed his coworkers. And after that, Thomson would sometimes, say nice things about some of Heaviside's work. Particularly in 1889, Thomson gave a well-known presidential lecture to the newly renamed Institution of Electrical Engineers, in which he praised Heaviside's work. but they didn't see eye to eye on quite a few things. As is well known, Thomson didn't really pick up Maxwell's theory much for a little while, but not much. As Heaviside said in a letter to his friend George Francis Fitzgerald, the elastic solid ether had crystallized the brain of William Thomson, that he just could not bring himself to accept the new Maxwell type theories. And so there's a little bit of patronage, but not as much. Heaviside's major patrons, or people who helped to bring him to a wider audience, were really younger physicists, what I've called the Maxwellians, and they called themselves that too, particularly Oliver Lodge and George Francis Fitzgerald, who really picked up on Heaviside's work, brought it to a wider audience, praised it, and sort of helped him out. Thomson, in his later years, said, "Oh, Heaviside was a nihilist. That he was not, he was just satisfied with equations rather than the real physical theory," which I don't think is quite fair to Heaviside. He was concerned about the real underlying physics, but they had some real differences in later years. And though Heaviside had enormous respect for Thomson, he thought that he was, by the 1890s, that Thomson was well well behind the leading edge of things.
Okay, I think we'll probably have only time for one more question. So could you talk a little bit about the work that led to the naming of the Heaviside layer? Was that Heaviside?
Yeah. Heaviside, actually in an article he had written for the Encyclopedia Britannica around 1900, a little after 1900, was trying to explain the rather surprising results that Marconi had gotten with sending radio signals across the Atlantic. How could they do that? If they're like light waves, they should just go in a straight line, and so they wouldn't go over the horizon. And Heaviside suggested that, and there was other reason to believe this, and Fitzgerald actually had suggested a similar idea, that there might be an electrically conducting layer in the upper atmosphere, where the atmosphere, it was known that in a rarefied gases that they can conduct electricity, as in a vacuum tube kind of thing. And so that there might be a conducting layer in the upper atmosphere, and if there was, that would allow the radio waves to bounce off or be guided over the horizon. And so this later became known as the Heaviside layer, or the Heaviside-Kennelly layer, after Arthur Kennelly in America, who made a similar suggestion. And in the 1920s, the Heaviside layer was much talked about. It was a sort of common thing you'd hear about. That's why you could pick up radio signals, very far away. I got to say, in the musical Cats, up to the Heaviside layer. That's where good cats go after they die. That's from T.S. Eliot's, a book of practical cats, where he's drawing on the idea of the public knowledge of, Heaviside layer was something to sort of a phrase people would know. I think Oliver, who died in 1925, Oliver Heaviside would have been deeply amused at the sight of a bunch of chorus girls dressed up like cats singing his name over and over again on Broadway or in the West End. But that didn't happen until after he had passed from the scene. So he's involved with the Heaviside layer, but only as a sort of theoretical suggestion of something to explain otherwise puzzling propagation of radio waves.
Okay, I'm afraid, regrettably, we're going to have to leave a few questions on the table. Thank you for posing them. But if
anybody wants to email me with a question, I'm happy to try to answer.
As you can tell, Bruce Hunt is very enthusiastic about his subject matter, and we absolutely enjoyed having you. Thank you so much, Bruce. It's really been a pleasure.
Thank you, Will.